few acknowledgments just right at the beginning. So this is the inaugural lecture of this Nauenberg History of Science talk. And this was started really shortly after Michael's death. And it was really very much initiated by the Nauenberg family and Todd Whitke, who at the time was president of the Emeriti Association. And they established a fund which would support this History of Science lecture, which we hope will go forward for many years. I especially want to thank all of you who donated to this fund. We've been a little slow in starting it because of the COVID era has made difficulties for this sort of big event, but we're really going to put it together tonight and get it off to a good start. So to really start our proceedings, let me see if I have any other items of business. Let me just say that you will be able to ask questions by going down to the Q&A box, which is down in your screen. You move your cursor to the bottom and the Q&A box should show up there. And just type in your question, and at the end of the lecture, we will handle as many of those questions as we can. All right. So with that being said, I would like to start the evening by introducing the person who will introduce our speaker and also say something about Michael Nauenberg. So this is Tony Tromba. Tony is a distinguished professor of mathematics. He was a good friend of Michael Nauenberg, and Tony knows a bit about the history of science himself. So with that, Tony, I'm going to let you start this inaugural first lecture, the Nauenberg History of Science lecture.
Okay, well, hi everybody. It's really a pleasure and an honor to introduce the first speaker in the Nauenberg History of Sciences lecture series. But before we turn to our speaker, I've been asked to say a few words about Michael Nauenberg. Unfortunately, I really need a book or two to describe in any depth the work of this truly extraordinary man whom I've known for almost half a century. So my task here is really a difficult one. In 1966, at the age of 32, Michael came to UCSC from Columbia and Stanford as a tenured professor, joining Bruce Rosenblum as the senior faculty members and founders of the UCSC physics department. With a famous theorem on particle physics under his belt, Michael had the reputation, the scientific connections, coupled with limitless energy and tenacity, all of which would enable him and others to build a first-rate physics department. In this endeavor, Michael was really tireless. He and Clem Hoysh, who had come from Caltech, founded SCIP, the Santa Cruz Institute for Particle Physics, as well as UCSC's Institute for Nonlinear Science. Within this second institute, there was a group working in chaos theory, a rather new field at the time, a field that had really captured the public's imagination. You all know the ubiquitous cliche: a butterfly flaps its wings in the Gulf of Mexico, causing a tornado in Oklahoma, something like that. Chaos theory even makes it into Steven Spielberg's 1993 blockbuster film Jurassic Park, where one of the main characters, mathematician, chaos expert Ian Malcolm, played by Jeff Goldblum, takes a role. As a mathematician, I was quite amused that Spielberg had T-Rex eat the lawyer and not the mathematician. Michael mentored a successful group of graduate students in this area, just to mention two of them. Doyne Farmer, now Bailey Gifford Professor of Mathematics at Oxford University and the director of the group on complexity economics. And then there was Jim Crutchfield, who is a distinguished professor at UC Davis. So Jim and Doyne had decided to work in certain aspects of complexity theory and chaos. And so they decided to test the theories they had worked out by going to Las Vegas and take a turn at the roulette wheels there. As a result of their experience in Las Vegas, a book was written called the Eudaimonic Pie that described their experiences. And this became quite popular. The bizarre true story of how a band of UCSC physicists and computer wizards took on Las Vegas. As a consequence of Crutchfield and Farmer's visits, Nevada passed a law banning the use of these such computing devices at their casinos. Michael's list of achievements is extensive, but in line with the theme of this lecture series, I will briefly focus on some of his work in the history of science, and will try to illustrate how really exceptional Michael's thinking was. So it was in 1971 that I met my dear friend Michael Nauenberg. Almost immediately, Michael started bombarding me with mathematical and historical questions, and he never, ever stopped. Unlike any other colleague I ever met, he was deeply interested in the origin and development of scientific and mathematical ideas. Like some other physicists, like Dirac, Planck, and Feynman come to mind. Michael was intrigued by the, quote, unreasonable effectiveness of mathematics in describing the physical world. As in James Watson's book, The Double Helix, the story of the discovery of DNA, Michael was also fascinated by the struggles, the intrigues, the dirty laundry, the character flaws, and not just the scientific end results presented in polished academic courses. So upon his retirement, he decided to focus on the history of science and mathematics, and in particular on the historical Big Bang, the very beginning of modern science, namely the 1686 publication of Newton's Philosophia Naturalis Principia Mathematica, or the Mathematical Principles of Natural Philosophy. In the 16th and 17th centuries, it was observed through the work of Copernicus and then Kepler that the planets moved in what appeared to be elliptical orbits, but no one knew why they moved in this way. It was hypothesized by Robert Hooke that this was a result of a force exerted by the sun upon the planets. Newton called this force gravitation after the Latin gravitas, meaning heaviness or weight. Hooke further hypothesized that the force of gravitation varied inversely with the square of the distance to the sun, but he was unable to prove this. In 1680, Hooke wrote a letter to Newton proposing an approach to solving the problem, but from what I heard, asked for some help, since he was mathematically unable to deal with its complexity. Hooke had needed to understand some of the very deep mathematical ideas behind what we now call calculus, but he simply could not get that far. Newton, the genius, on the other hand, had already, as a student at Cambridge, developed the calculus. Newton was able to show mathematically that elliptical orbits were indeed a consequence of the inverse square law, and a solution appears in the Principia. But the solution in the Principia was a geometrical one and not an overtly calculus one. Whether or not Newton first used calculus to solve this problem has long been debated, as was Hooke's real contributions to Newton's achievements. With regard to Hooke's contributions to what we now call orbital dynamics, Newton suppressed these as well as Hooke's other contributions. I am told that Newton, as president of the Royal Society, went so far as to destroy all known portraits of Hooke. And as far as I know, none exist. So Isaac Newton attempted to relegate Robert Hooke, for whatever reason, to oblivion. 3 centuries later, Michael Nauenberg decided to bring Hooke back from oblivion by reconstructing Hooke's significant achievements in orbital mechanics. Then once again, pushing against general historical consensus, Michael argued that Newton had to have first used calculus to derive the elliptical orbits of the planets, and later disguised his methods. Michael also got involved in the brutal calculus war, lasting nearly a century, a war between English and continental scholars over whether Newton or the German philosopher Gottfried Wilhelm Leibniz had discovered calculus. Why was the discovery of calculus such a big deal, worth fighting over? Well, if the Principia is the beginning of modern science, then calculus could be considered the beginning of modern mathematics. 2,400 years ago, the ancient Greeks lifted the veil from the understanding of the natural world. Astoundingly, they discovered mathematics, mostly geometry and number theory. Then, in a huge leap of imagination and a giant step forward for mankind, they came to the conclusion that the natural world was not incomprehensible. Just the opposite, the natural world could be understood. Moreover, the natural world followed laws, and these laws were mathematical ones. Newton took it further, saying that the laws of nature are differential equations. That is, equations in calculus that describe the behavior of physical systems that evolve in time. When one considers Newton's differential equations of orbital motion, Maxwell's differential equations of electromagnetism, which ushered in the modern communications age, Einstein's differential equations of general relativity, which dispensed with Newton's gravitational force and gave a new model for the structure of the cosmos, and Schrodinger's differential equation of particle physics, ushering in the age of quantum mechanics and the probabilistic view of the universe, and on and on and on, one then comes to realize how very extraordinary the creation of calculus was and how prophetic Newton turned out to be. Most scholars have given equal credit to both Newton and Leibniz for the discovery of calculus. Michael then turned everything topsy-turvy when he convincingly argued that neither Newton nor Leibniz deserved the credit for this discovery. For his deep contributions to the history of science, Michael was awarded UC's Constantine Panuzio Prize for scholarly work done as an emeritus, the only scientist ever to have received this recognition. This wonderful Nauenberg lecture series, supported by contributions from the Nauenberg family and the Emeriti, is now a neutron star, the remnants of the goal for UCSC that both Michael and I shared for over 40 years. The goal to build a history of science and mathematics program at UCSC, a program showcasing the breathtaking story of the brilliant developments in history of mathematics and science that brought us to a modern technological civilization. So at this point, I would like to introduce our speaker. It's a great honor for us to have as our inaugural speaker, the distinguished Caltech historian Jed Buchwald, Henry Dreyfuss Professor of History, MacArthur winner, and former director of the Dibner Institute for the History of Science and Technology at MIT. That's Michael's alma mater, by the way. Jed is a member of the American Philosophical Society and the author of 6 books, many articles, and 1 movie on Isaac Newton, Nova's documentary, Newton's Dark Secrets. Going through the internet, I discovered that Professor Buchwald is also an actor. He brilliantly plays the mathematician Joseph Fourier, who discovered the differential equation of heat transfer. So now I welcome Professor Buchwald, and let's all give him a hearty welcome. Thanks a lot.
Thank you. I think we're on.
You are.
Especially in honor of my old friend, Michael Nauenberg, whom I've known for over 30 years. And I miss him very much. He and I often spent many, many hours discussing things in the history of science and other things. We didn't always agree, but not agreeing with Michael meant you really had to defend yourself and defend yourself well. He was iconoclastic, brilliant. He saw things that others did not see and worked hard to convince people about it. He did convince me about a lot of these things. And towards the end of my talk, I will tell you a little bit about some of them so that you can really see what it was that Michael was able to do that had not been done before. But today, or tonight, I'm going to be talking about a different Newton. A Newton who, in retrospect, seems someone very, very different from the author of the calculus and other things. And now to begin, I will try and share my screen and hope that you can all see it. This is a portrait of Isaac Newton in his prime. I'd say he's about 48 or 49 years old. This is the Newton just after the publication of his great Principia Mathematica, many years after his youthful work on the calculus and other unrelated materials. This is the man we mostly know about and hear about in the history of science. Here we see the frontispieces of his two great publications, the Principia Mathematica, written, as you've heard, in geometric form, but deploying nevertheless the concepts that underlie Newton's development of the calculus, published in 1687. And then in 1704, his great work on optics, widely read, translated into many languages, and accessible because it develops the other major strength that Newton had that I'll talk about a little bit in a few moments, namely his deep and concrete involvement in the actual experimental practice of science. There are a number of aspects of experiment which actually originate with Newton himself. But let me take you back first to when he was a very, very young man, when he first entered Cambridge University. Here's a portrait from around that time, well, done a little bit later, actually. He was born in 1642, and he lived a long time for that period, died in 1727. And he grew up on a manor house in the countryside in a town called Grantham, northwest of Cambridge. And from a very early years, he showed a tremendous aptitude for the building and construction of various devices, but not much by way of academic interests. He did eventually get sent, went up to Cambridge, as it said, and there for the first few years, he actually was not showing much interest or concern with physics or mathematics until he attended the lectures of the professor of mathematics there, a man named Isaac Barrow, of whom Michael Nauenberg actually in whom he was quite interested. And Barrow saw the genius in this young fellow and pulled him in. Newton eventually edited and helped his work in various ways. That pulled him in to the rapidly developing world of the new sciences, the world of the mechanical philosophy, a world in which the universe is considered to be structured according to matter and motion in various ways. And he began studying such things. And we have his notes from when he was a young man. Let me show you a picture taken of one of them. What you see here on the left is from his student notebook. You'll note that there's a hand which has a stick, and it's pushing under the bottom of the eye, pushing up on the eyeball. He actually did this. I always have to warn my students not to try it, but you can see in the other pictures on the side what he's up to. This is the beginnings of his experiments with light. And what he's doing on the left, which is important to understand, is he's probing the ways in which the senses can provide deceptive information. By pushing on the eyeball, he could generate little colors that, if you can see my cursor, are shown up here. These are nowadays called phosphenes. And that leads him to think of the senses as no more inherently reliable than well-constructed instruments. They are, in effect, organic instruments. And because of that, he was able to design and develop and work experimentally, even at such a young age, in ways that others were not able to do or did not occur to them to do. This brought him directly into contact with the manipulative character of the experimental world and distanced him as well from the world that he had first encountered at Cambridge, the world of scholastic philosophy, which he had studied in the usual veins of the time. Here is a page from a Newtonian manuscript. These things are often hard to date, but this dates from probably around 1666, 67, maybe a little bit later, in which you can see algebraic structured calculations on the left, what looks like an ellipse on the right. It's his first mathematical engagement with planetary motions, dating at a very, very early era. There's no conception of gravity or anything here, but it shows you how rapidly this young fellow was able to work. I doubt there were more than 4 or 5 people in all of Europe who could actually work the mathematics that you see on the right there. And he was, at this point, maybe 25, 26 years old. But this did not hold his interest for that long. Instead, by 1669, 1670, when Newton had become the Lucasian professor at Cambridge, a position he acquired when Isaac Barrow, who was the first Lucasian professor, stepped aside to let Newton take that position, having recognized his genius. Newton's interest instead was turning in a different direction, a direction that concerned the empirical world indeed, but the question of the transformations of matter. And he engaged in what, in retrospect, looks like strange alchemical operations. It was a process which at the time was called chemistry, the question of not necessarily transforming things into gold, but trying to understand how chemical manipulations might work to produce different amalgams of various kinds. And he worked this vein for years. Here we see a page from his manuscript reproduced there a little bit. It looks very strange. You see what it says. I'll read that to you. Excuse me a moment. Mars and Saturn, behold his face, into which will seem fresh and young when the souls of both, et cetera, blended together. Well, it does look strange. This is actually a chemical recipe. It's a recipe for producing a very significant result called the star regulus. A colleague of ours in history of science at the University of Indiana, William Newman, has actually been able to reproduce these things. And what that is a recipe for is this, the star regulus, one of the amalgams that can be produced. And so Newton spent many, many hours working at his chemical furnace, working to see how things could transform. Not mysteriously, he thought that the ultimate grounds of transformation had to do with little particles of matter, and he was trying to figure ways to rearrange them and so on. Of course, couldn't do it with a nuclear furnace, but nevertheless, he progressed fairly far, and it was rather strongly influential in the way in which he came to understand aspects of planetary motion, mechanics, and gravity later on. But there was another aspect to his work, which was also beginning to show itself a little bit at this time, not too much, but a little bit. He had become quite concerned with the way in which the world had evolved and civilization had developed. I'm going to give you more details about that in a moment, but let me take you to where this eventually resulted. Towards the end of his life, in fact, the very last thing that he saw before his death was this book here, The Chronology of Ancient Kingdoms Amended, the roots of which go back to his earlier years. There you see Newton as an old man on the right. And this was published just after his death. And in this book, Newton attempted to redate the entire history of civilization. And he did it in a way which rested directly on two things. One, astronomical calculation, and two, his deep felt skepticism about language and words. He found them, and he is, of course, not at all unusual in those days, untrustworthy. So I'm going to try and take you through what was beginning to drive him, what eventually produced this result, which was at the time quite influential, as we will see. So let me take you back to some of his early manuscript writings on it. They really didn't start until sometime in the 1690s, and I will tell you about Newton's career in the 1690s shortly. Here is a manuscript page dating from around that time. And what is it? This is a genealogical chart of Greek gods and humans. What's going on here? Newton's deep skepticism of words and the myths and mythologies that humans create meant that for him, anything from antiquity that was reliable about gods or humans had to be transformed into a story about actual people who lived, or else discarded altogether. And here is his earliest attempt to try and link up a series of the Greek deities in ways that might give them some sort of naturalistic structure. The procedure came to be known as euhemerism, attempting to import humans into mythologies of the past. And Newton, as we'll see, worked this vein very strongly. But he wasn't the only one, because in those days, there was growing skepticism about taking the literal words of the Bible as they stood. So that although Newton is a deeply religious man, as we will see, although actually something of a heretic, given the standards of the day, nevertheless, he and others did not think that there was ever anybody who had lived 900 years or various other things. And so there were people who were attempting to try and understand what the natural course of human lives had been, and indeed how to fit the chronology of civilization into such a context. Now, let me say at once, of course, this doesn't mean that you can find almost anybody who thinks the universe is older than about 6,000 years. But the question is, what happened after that? Here is a manuscript from around the time that Newton was beginning to get into things by a man named Gregory King, who was concerning himself with the question of the rate at which human population could have grown since the Noachic deluge, which Newton and others still put a credence in, although the question of when that happened is a different matter. And here you can see King's attempt to actually work with a natural human lifespan and to see how, on such a basis, the world could have been repopulated given the timing available. Didn't work very well. Now, at the same time, you also had, or shortly before, extensive works on the history of the world. And here is a very important one. We know that Newton read it by a man named Dionysius Petavius. And here you see this is published in 1659. And notice that it says not just the history of the world, but an account of time. The attempt to develop a workable, understandable, naturalistic chronology and to correlate that with acceptable remarks from antiquity and with the remarks, especially from the Old Testament. Newton read extensively in material like this. And here is a book we know that he read because what you're looking at here is actually the frontispieces of the very copy that he owned by John Marsham, a canon chronomicus, a chronological structure of the Egyptians, the Hebrews, and the Greeks, running it through and trying to collate all of these things in a way that made sense. Newton read this very, very carefully. How do we know? Well, because we know, since many of his books and notes remained, that when Newton was interested in a particular page in a book of some kind, he would dog-ear the pages. And here, in this particular book of John Marsham's, you see the pages dog-eared. This is Newton's dog-earing. And where those points point to, so to speak, are the very passages that gripped his interest intensively. This was Newtonian note-taking. And he would copy things down, think it through, and try and come up with his own scheme for how such things work. He developed a claim concerning the development of monarchies. And here you have, I'm sorry, it's not a very good reproduction, a page from one of the first things that he wrote, the Original of Monarchies, in which you can see what he's beginning to do. The whole world was, by the first inhabitants, divided into many coordinate governments according to the numbers of families. Well, what is involved in that? It's this. He runs through this and develops an entire scheme for the way in which human civilization would have evolved. And we can diagram that scheme, and it looks like this. You start with growing population according to natural laws. As things progress, towns evolve as groups get together. The towns, in order to be governed, come under the control of an assembly of what he called fathers. These produce groups of laws. To administer the laws and carry out their efficacy, they require a judge. The town with court and judges gets bigger, evolves into a city. The city has villages that emerge to support it through food, agriculture, and crafts in the surrounds. The city judge enlarges his authority, transforms thereby into the king of the city and the villages, and then kingdoms emerge by enlargement, by conquest, or merger. This is Newton's scheme, and it's not a bad one, for the evolution of civilization on the basis of what he thought would be a relatively naturalistic structure. And he thought that civilization first acquired its firmest structural development into a kingdom under Solomon in Hebraic antiquity. Here you see a later portrait of the Judgment of Solomon by Giuseppe Cades in the 18th century. Well, one of Newton's acquaintances, William Stukeley, wrote shortly after Newton died, just a few weeks actually, wrote the following. He says, Newton says that Solomon's temple was older than any other great temple, that Sesostris, that is an Egyptian pharaoh, from this model built his temple in Egypt, and that from there the Greeks borrowed their architecture, as indeed they had their religious rites. In other words, it all started in antiquity with the Davidic kingdoms, according to Newton. And he was quite convinced about this, so convinced that he spent a good deal of time trying to figure out what the measurable techniques were that led to the construction of what he thought was the prototypical architectural temple, the model of all others, including Greek temples at the time, namely Solomon's. And here you see a page from Newton's manuscript in which he attempts to reconstruct the structure of Solomon's temple. This manuscript, by the way, is today held in the Burndy Library at the Huntington down here in Pasadena, San Marino, actually. And he wrote extensively on this, though it wasn't published until after his death. And here is a work that was published after his death entitled The Dissertation on the Sacred Cubits of the Jews and the Cubits of the Several Nations, in which from the dimensions of the great East Egyptian pyramid, as taken by somebody who had gone there, John Greaves, the ancient cubit of Memphis is determined. Newton is trying to figure out what the original unit was for the construction of these great objects from antiquity. And he thought that it was first produced in order to construct the Solomonic temple. Well, Newton, though, at Cambridge, from his early career on into the 1690s. In fact, over here in this picture of Trinity College, if you look in the, I don't know if you can see my cursor, in the corner over here, on the far left corner over here, those are where Newton's rooms were and where he carried out his alchemical experiments. Well, in 1686, James the King, James II, dismissed the vice chancellor of Cambridge University. This did not sit well. When Magdalen College at Oxford refused to elect a Catholic as president, James usurped its rights by expelling the fellows and appointing Catholics in their place. Now, he didn't plan to make Magdalen an exclusively all-Catholic college, but he had broken the usual monopoly among the professors at the time, and in a manner which allowed him to be depicted as an enemy of academic freedom rather than a support of academic freedom. Well, this generated a huge result. In fact, the Glorious Revolution, which deposed James, and Newton was consulted along the way in quite a bit of this. This is what really first brings him out. He's well known among mathematicians and other scholars of the day by this time. And his Principia is about to be published the next year. This brought him out into the real world, almost. He was elected to serve in Parliament. It is said that he only said one thing during the term that he served in Parliament. He asked that a window be opened because it was too hot. Never said anything else, apparently. Eventually, though, he was pulled into the maelstrom of London. This is where Newton lived, in London. It's still there on Jermyn Street. He lived there from 1696 to 1709. You can see the blue plaque on the front. If you go to London, you can walk right by the house. I took this photograph some years ago in London. Now, when he was brought to London, when he came to London, he was actually brought there as warden of the mint that produced English coinage. And he was needed because they were undergoing very difficult times involving counterfeiting, or what was called coin clipping at the time. Since these coins were silver, sometimes gold, you could clip little pieces out of them and do that on a lot of coins. You can accumulate a lot of things. So Newton was brought in as warden of the mint and eventually became master of the mint. And there you see him on the left, dressed up in the regalia of the period. He designed new coins of the reign of the time. When William became king, following James II's removal, these coins on the left were designed by Newton. Then after William, Queen Anne, you see those designs there. And then for George I on the right in 1717. So he was deeply involved, but not only in that, and this is going to bring me to something that's of direct relevance for my main topic here. He also was in charge of chasing after counterfeiters. This is actually a manuscript containing the testimony of one Catherine Linton concerning her involvement with somebody whom Newton and others suspected of being involved in counterfeiting. You can see Newton's signature on the lower left. Newton caught counterfeiters, and the punishment for counterfeiting was death. And Newton sent people to the gallows at Tyburn in Westminster, in particular, the notorious counterfeiter, William Challoner, who was caught and convicted by Newton at the time. Not a nice story, although I must say that Challoner was not a particularly nice character, as it turns out. But nevertheless, this was characteristic of the period, and it shows you how deeply involved he was. Now, what has this got to do with my main point? Well, in engaging in interrogations and so on, Newton's deep suspicion of words, of the trustworthiness of testimony, whether it's on ancient documents or taking the testimony of counterfeiters, was exacerbated extensively. And it is only just at around this time that he becomes profoundly engaged in attempting to reduce the words of antiquity, to the extent that they were reliable at all, to numbers, in particular to the one thing that he really put trust in, numbers that could be connected to things that happen in the world, in particular to astronomy. Again, he wasn't the only one who didn't trust words. There are many famous remarks. Here's Francis Bacon: the faulty meaning of words not only make discourse tedious, but they impair judgment and understanding. John Locke, Newton's friend: the very nature of words makes it unavoidable for many of them to be doubtful and uncertain in their significance. Later, in the 18th century, George Berkeley: we need only draw the curtain of words to behold the fairest tree of knowledge. Words, they thought, they felt, block knowledge. And here's Isaac Newton. While the Greeks wrote only in verse, there could be no chronology, nor any other history, that is, nothing reliable about the past, than such as was mixed with what he called poetical fancies. And his goal was to strip out all of the poetical fancies from the remains of the writings of antiquity and to transform them into things that were not poetical in his view, namely numbers, numbers concerning the heavens, which is what he set out to do. And in order to do that, of course, he needed the words of antiquity. Now, there aren't many. In fact, the greatest astronomer of antiquity before Ptolemy lived in the 2nd century BCE, a man by the name of Hipparchus. Now, unfortunately, we don't have anything directly from Hipparchus, but there was a text written by a man named Aratus, which gives you sort of a tour of the heavens. It was often used by Greek and Roman aristocrats to train their children. And in it, he quoted some of the things that Hipparchus had said. And here you see the first printing of this text in 1567. Now, Newton relied on this, only he tried to strip away, as I've said, everything unreliable from it. And we can see a number of the things that he was doing. There was the text of Aratus, and I'm going to tell you in a few moments the details that he took from it, and other remarks from antiquity, for instance, from Clement Alexandrinus, Clement of Alexandria, that's the 2nd century AD. Let me read you what Newton wrote about that. This was published in his chronology. And let me just take a few points out of it. Chiron delineated the asterisms, the constellations. Chiron was a practical astronomer. And one of the Argonauts made a sphere, Jason and the Argonauts. We're back into the myths of antiquity, trying to strip things from them that you could use. And the sphere itself shows that it was delineated in the time of the Argonautic expedition. Now, if this were true, if this sphere of the heavens was designed and used by the Argonauts, designed by this character Chiron, then maybe you could use what was on that sphere to date when the Argonautic expedition occurred, and that would be a reliable way to work. Let me show you who Chiron, the practical astronomer, was. This is Chiron the centaur. But given what I just told you a few moments ago, Newton's inveterate euhemerism, he, of course, doesn't think that there was a half man, half horse. No. Chiron was a man around whom the Greeks had built poetical fancies. So now Newton is going to try and turn it into something that's not so poetical, and how to do that. And so now I will show you what he did. So what I've drawn here is a rude depiction of the heavens. Imagine the heavens as a giant sphere. And imagine that we're at the center of the sphere. This is not because Newton doesn't think that the Earth goes around the sun, but for observational purposes. Then the sphere rotates around a plane called the equator once a day. And here we are on the Earth at a certain latitude, and I just drew in an arbitrary horizon line. And among the stars, the planets and the sun move during the course of the year. They change their positions among the stars, and they move in a plane called the ecliptic, and that is the plane that contains the constellations of the zodiac. And many of the remarks that Newton was going to use concerned positions of things with relationship to the ecliptic, the zodiac, and to two particular other planes. If in this great sphere you drew a plane that ran through the solstices, that is the solstices during the summer and the winter, and another plane that ran through the equinoxes during the fall and the spring. These are planes which intersect the ecliptic, as you can see, and many of the remarks in Aratus concern the constellations where these intersections occur. So you might be able to use this to create such an issue. Now, how can you do that? Well, you can do that because things shift around in the plane of the zodiac as a result of what's known as precession. What is precession? Well, the Earth is a spinning top, in effect, and the action differentially of the sun and the moon on the Earth, effectively speaking, cause the axis of the Earth to rotate around, forming a conical motion, which is slow. It's about 25,920 years to go all the way around, but that's 1 degree every 72 years and was already known to the Greeks. Hipparchus, for instance, thought it was about 1 degree every 100 years. That gets refined over time. And astronomical observations go way back. And it is this, by calculating back using the rates of precession and coordinating it with the reinterpretation of Aratus's text using astronomical computation structures, that Newton is going to attempt to redate the past. Now, in fact, what I've plotted for you here are the positions of the summer solstice along the constellations running in the past, starting around 1800 here. But if we go all the way back to 5000 BCE, we can see how it's moved along. Here it is around 2000, around 1000, then around the time of Christ, then 1000 of the Common Era, and so on. It moves quite a bit, and therefore there's plenty of possibility of using this development to date the past, which is what he does. Now, among the things he uses, in addition to Aratus, are other remarks. In the Aratus itself, he finds the statement that Hipparchus, quoted by Aratus, tells us that a Greek mathematician by the name of Eudoxus drew the collier of the solstices, that great circle that I just showed you a graphic of a moment ago, through the middle of the Great Bear, the constellation, in the middle of Cancer, and the neck of Hydrus, and so on and so forth. Can we do something with that? Can we do something with that? Do we have a picture of these things from the past? Well, actually, we don't really. There's only one such thing that was known. It still exists. This is a photograph I took this past summer in Rome of it. It's called the Farnese globe. It dates from about the 2nd century CE and depicts the constellations. It has been argued that actually the depiction of the constellations on the Farnese globe represent their distribution at the time of Hipparchus. That remains controversial for reasons that are going to become clear in a moment. When you say something like the collier of the solstices passed through the back of the Great Bear. Where is that? And what is the Great Bear? Well, here are some depictions of constellations today using some modern software to draw a grid and put them up there. Well, there's Ursa over here, Leo down here, Cancer the crab, Gemini over here. Well, that's all very good, but what were these depictions like in the past? Did they look like this? Well, we do have some data, not all the way back, but certainly back to the Middle Ages. So let me show you some of them. Here is what Cancer and Leo looked like to someone drawing in the 12th century. Not very much like what you just saw a moment ago. Here is part of the depiction of Gemini, the twins, in the 9th century, much earlier even. And here is a Persian depiction in the early 17th century of Gemini. Doesn't look much like the two up at the top. And notice in both cases, you see little gold dots here and little dots, black ones over here. Those are stars related to various positions on these depictions. And here's a depiction of Gemini, or at least half of Gemini, in 1627, before Newton's birth, by the German Schiller, depicting St. James as Gemini. And here is the depiction Newton used from a famous atlas, widely used, printed in 1603 by Bayer, again depicting Gemini. And then if we go a little bit further to 1729, 2 years after Newton's death, by the royal astronomer John Flamsteed, there is Gemini. Now, if you say something about, let's say, Gemini, let us say the collier of something passed through the shoulder of Gemini, exactly where is that going to be in such a depiction? Lots of possibilities. Well, in order to do this at all, Newton needed to work up calculation techniques for doing such things. This wasn't his original area of study, but he's, shall we put it mildly, a very fast study. This is the text that he worked from, published in 1669 by Street, the Astronomia Britannica, which contains logistic formulae for astronomical ephemerides, locations of planets, and so on, easy trigonometric techniques for spherical trigonometric calculations, which Newton was very good at anyway, as well as planetary motions, so that you could calculate things back. Newton is not going to use the motions of the planets on ellipses in the Principia. He needs observational work. He's going to work from a geocentric and Earth-centered position to try and figure things out, to coordinate data from the past with these things. Now, he needed the best coordinates. At this point in time, the most accurate coordinates of the stars had been produced by a German brewer, actually a Polish brewer, by the name of Hevelius, Johannes Hevelius, in Danzig, who became fascinated, and he was wealthy. And you can see on the right, one of the very elaborate instruments that he created. And he created an entirely new catalog of the stars, their positions, the most accurate one. And this is what Newton worked with at first. And here you see a publication of Hevelius's stellar catalog from 1690 and so on. And we even have the manuscripts for this thing. The manuscripts are actually held at in Utah at the moment at Brigham Young University. Complicated story as to how they got there. Somewhat better coordinates Newton was desirous of having could be obtained from this fellow, John Flamsteed, whom I just mentioned, the Astronomer Royal. Over there, you see a photograph, contemporary now, of the Royal Greenwich Observatory. And Flamsteed was working on new coordinates. He didn't really want to let loose with them, but Newton's young friend, the astronomer Edmund Halley, and Newton managed to extract these coordinates from Flamsteed against his wishes. And these coordinates then could be used to update the ones that Hevelius had produced, giving Newton the data that he needed to work with the words from the past. Now, if we look just at Newton's final published book, the chronology, you really wouldn't be able to figure out what he did. But in fact, we have all of his manuscripts. He was an inveterate note taker. He'd use the same piece of paper sometimes for years, which can make it difficult to date things as to when he was doing what, but you can figure things out. But let me show you an image of a typical page in one of Newton's manuscripts. This is one. Notice what it is. He's writing all over an invitation. You're invited to be at a court to be held in, that's at Christ's Hospital on Tuesday, et cetera, et cetera. And of course, he's not going to throw out pieces of paper. Paper is valuable, difficult to get. And you see scribblings all over it. It's typical. There are actually some computational remarks hidden in the scribblings on the right, and others on other pages, and you have to take them out of pages that look like this. And if you do, you can get things that look like this. And this is what my colleague Moby Feingold and I, when we wrote a book on this, I had to work through this to interpret back what this computation is all about. And here you see lists of zodiacal positions on this scrap here, a total number of them. And what is he actually doing with this? What does it mean? We know, or I knew, that he wanted to calculate back to the past using these remarks from antiquity. And how did he do it? Well, searching further, there are many, many other pages, and you see pages that look like this. Now, this is actually one of his computations. I'm going to briefly show you what that is in a moment, but you can notice that it's, these are actually in degrees, minutes, and seconds over here. These are actually logarithmic functions, trigonometric functions of these things, with final results and modifications of them. And it's technical what he's done here astronomically, but let me just briefly show you. When I translated this and figured out what it was, this is what he's done. He's calculated the point of intersection of the collier on a latitude that is parallel to the ecliptic at a certain time. And these calculations in here are calculations of the spherical trigonometric sine of this distance here on the stellar sphere. He takes these ratios and then he uses a table of logarithms, and I was able to find the table of logarithms that he uses in order to convert the computations into numbers that he can then use. So this is how he's working. And what are the results? Taking so many of these remarks from the past, the collier through the back of the Great Bear, and assuming that he could position that. And how did he do that? When I showed you that there are so many different depictions of the Great Bear, he thought that if the remarks are meaningful at all, if you said the middle of the Great Bear, you probably had to mean the middle of two prominent stars in the Great Bear, which is how he worked. He always immediately cut through to try and interpret what are pretty vague remarks, given that you can draw these things in multiple different ways to produce his results. And what did he obtain? Well, here's what he obtained. These are the results he obtained from these remarks in Aratus about these colliers and so on, using these various structures. And these are the dates that he comes up with. One of them is rather later, by about 100 years, but they're all circulating around sometime around 970, 980 BCE. That, Newton thinks, is the date of the Argonautic expedition. That's close to 500 years, 400 to 500 years different from what philologists had obtained at the time. Newton also did something that nobody else did at the time. That is, he processed the set of data by taking an average to find out what he hoped would be a reliable number. This was controversial. Statistics had not been invented yet. There's no fundamental rationale for that. And in fact, it was challenged later in the century and so on. But nevertheless, he felt that it was a good measure by analogy with finding the center of gravity of weights is the analogy that he used. Now, in fact, let me turn to this slide here. There is an astronomer by the name of Bradley Schaefer at Louisiana State University. Professor Schaefer did not know that Newton had used these remarks in Aratus to come up with these dates. He decided to do it himself without, as I say, knowing that Newton had done it. And so he recalculated things using these Collier remarks and so on. And what did he come up with? 1600 BCE. Totally different from Newton because of the vagaries and how you can interpret these things. Now, you can see here, that was the original was 1600 all the way back, the most reliable, but then working it further, Schaefer pushes it, and you can see the tremendous variation in the dates that he comes up with in this structure. So this is a kind of experimental test that one can use to see in retrospect what Newton and today what Schaefer were doing in reinterpreting these remarks from the past. They're not usable data, but if they were to be used at all, they had to be used in this fashion, thought Newton and Schaefer. But there was more data that Newton had in his inveterate way of turning everything into numbers. Here you see a manuscript on the left, which contains the regnal dates of the Old Testament kings. What's he doing? He goes through it, trying to figure all of the regnal years of these kings to figure out in a total regnal length so that he can then come up with an average regnal period of 18 or 20 years, which allows him to recalculate various things, such as the 18 kings of Judah who succeeded Solomon reigned 390 years, which is one with another 22 years of peace, 15 kings of Israel after, et cetera, et cetera, et cetera. Again, constantly working to process the numbers, in this case, to do it by obtaining an average, which he figured would have to be a reasonable estimate because they weren't going to differ from one another gigantically. They're all humans with a certain mean lifespan. But now I'm going to show you something that tells us what it was that's running through Newton's mind as he reads these things, how he interprets things. Here is a remark from Newton's published chronology. We have this in a manuscript as well, in which he says that Hesiod, a Greek poet, there's a bust of him on the lower left from antiquity. Hesiod tells us that 60 days after the winter solstice, the star Arcturus rose just at sunset. And thence, says Newton, it follows that Hesiod flourished about 100 years after the death of Solomon, or in the generation or age after the Trojan War, as Hesiod himself declares. This is not an easy computation to make. Newton was able to actually use a technical method of doing it, which was available in a widely used text by Gian Battista Riccioli called the Almagestum Novum. There on the lower left is the system of coordinates that you'd have to use in order to work this Arcturus calculation. And so here then we see that he's interpreting things in a certain way, but what is he interpreting? Let's take a look. When did Hesiod then flourish? This is Newton again. Hesiod flourishes in 870 Why? And he's told us that he lived in the age next after the wars of Thebes and Troy. And Newton says this is what Hesiod said, and that this age should end when the men then living grew hoary and dropped into the grave, when they had a lot of beards and so on. That's what Newton isn't saying that Hesiod said. But is that what Hesiod said? No, this is what Hesiod said. He wrote, Zeus will destroy this race of men when they come to have gray hair on the temples at their birth. But you see, in Newton's way of thinking, that if this means anything, you have to interpret it to make it work with the natural course of human lives and existence. And so he must have been talking about old guys, not impossible children being born as old guys. And that little drawing on the lower right, there's some child made to look something like Albert Einstein, apparently. Well, the book was handed to Newton on his deathbed. He had somebody who had replaced him for a while at Cambridge, a man named William Whiston. And Whiston knew early on what Newton was up to, but he was very angry with Newton. And the reason was this: Newton had, as it were, worked himself into a Christian heresy by the time he was in, maybe around late 1690s, in his late 50s or thereabouts. What do I mean by that? Newton did not think, and this is consistent with his entire way of thinking, that the deity, all existing, all powerful, occupying every part of space, would ever, except rarely after creation, have intervened in the world. Occasionally, the deity might intervene, as the deity did, thought Newton, when he gave a human by the name of Jesus certain powers, but the deity never, as it were, became incarnate. Newton felt that that was would have taken away from the deity's power. This is an old notion, dates back to the time before the Council of Nicaea in the 4th century AD. It's known as the Arian heresy because it was pushed by Bishop Arius, and the Council of Nicaea decided instead in favor of the doctrine of the Trinity as pushed by Bishop Athanasius at the time. And Whiston was angry because Whiston was also an Arian, but unlike Whiston, Newton wouldn't talk about it because you could still get into trouble talking about it. And Whiston talked about it all the time. In fact, he had to leave Cambridge. He was lucky he wasn't talking about it 20 or 30 years before, when it was still a hanging offense. And so, angry that he was, he wrote a criticism after Newton's death of Newton's works, including a work that is related to the one that I just showed you. Newton wrote a text on the prophecies of Daniel, observations on the prophecies of Daniel, again, reinterpreting everything in these naturalistic terms. Let me just show you what Whiston wrote here. First, Newton. Newton had written in his chronology, as I've emphasized, that the Greek antiquities are full of these poetical fictions. You have to turn it into numbers. Well, Whiston knew Newton thought like that and had said that. And so, in trying to get back at him in a rather nasty way, Whiston writes the following: "We're now past Sir Isaac Newton's principal real arguments and must come to those of Newton that are poetical." Whiston is accusing Newton of doing the very same thing that Newton was effectively saying the Greeks did. Not very nice. But his chronology, Newton's chronology, was influential. It was drawn on globes that were widely sold. The most famous of the globes of the period, many exist still today, made by John Senex. These are celestial spheres, globes of the celestial sphere. And in fact, if we look closely at one of them, and I bring it up here, he has drawn in here Newton's collier. If I blow it up a little more, it says in Latin, Circulus, translating the Latin, it says the equinoctial circle, as it was situated in 939 BC, at which time, according to Newton, Chiron, the centaur, formed the constellations for the use of the Argonauts. So it was influential and widely known at the time. People wrote about it. Here in France, 2 years before Newton's death, this fellow Saussure had, through another man named Frere, gotten his hands on a manuscript Newton had allowed to be circulated, although Newton got very angry that this got into the hands of the French at the time. And this fellow Saussure, who is a philologist and historian of the period, writes an account and a critique of it. There was this text written by a rather interesting prelate by the name of Jean Ardouin, lived between 1646, 1729, just shortly around this time. He heard about this chronology, says the foundation of the chronology of the Englishman, Mr. Newton, published at London in 1726. It begins by saying, we never cease debating about the age of the world and so on. Well, in fact, Ardouin had his own views about the age of the world because he thought almost everything from antiquity had been cooked up by a bunch of forgers sometime in the 13th century. And he's an interesting character, but one suspects that he may have imbibed a little bit too much in one of the monasteries that he frequented at the time. There were others. Here is a book by a man named Arthur Bedford called Animadversions on Sir Isaac Newton's book entitled The Chronology of Ancient Kingdoms Amended. It's a critique. It starts off very politely, the learned Sir Isaac Newton, et cetera, et cetera. But by this time, it's 1728, there's a little bit of an odor about Newton's religious convictions. As I said, he was kept quiet about it, but he was an Arian. And this character, Bedford, may have gotten wind of it. And in any case, he didn't like what Newton was playing around with, particularly the parts that involved working with the Old Testament and so on. But it's perhaps not surprising because Bedford was also the author of a book entitled The Evil and Danger of Stage Plays in 1706, not one to allow people to run outside the acceptable bounds of the day. Then we have here Jonathan Edwards, briefly the third president of Princeton, deeply involved in the so-called Great Awakening of Christianity, Presbyterian Christianity in the United States. He lived between 1703 and 58. He refers to Newton's chronology in arguing that mankind cannot be much older than is represented in Scripture. Why is he saying that? Because at the time he's writing this, long after, 10 or 12 years after Newton's death, arguments concerning the age of the world had begun to crop up in various ways by various people, especially the philosophes in France. We have a critique, although a respectable one, by the young philosophe Voltaire in 1728, the year after Newton's death, who says it seemed to Newton the world was 500 years younger than the chronologists had it, which he based on the ordinary course of nature and astronomy. I don't know whether his system will have much luck. Maybe it'll be thought too much to accord to one man the honor of having perfected all three of physics, geometry, and history. That would be a sort of universal monarchy. Well, after Newton's death, poems were written about him, books were written, the chronology was widely read, debated about. And shortly after Newton died, the proposal was made to build a monument to him and to put his casket in Westminster Cathedral, where it sits to this day. Here's a photograph that my colleague, Modi Feingold, and I took, about 10 or 12 years ago, of Newton's sarcophagus and what was built around it. It's a bit of an amusing story at the time because you're not actually allowed to get close enough to photograph this thing. And one of the ministers, we contacted one of the ministers and told him we were professors from America, wanted to do this. And actually, we didn't say professor, saying that we were writing about the period. Would it be possible to take this? And he said, oh, yes, yes, yes. He was very kind about it. Then we went to go see him in his office afterwards when we found out that he was so enthusiastic about it because he thought we were writing a sequel to the Da Vinci Code of some kind. But in any case, we were able to make this photograph. And if we look closely at this photograph at Newton's tomb, and I zoom in, which is why I wanted to get closer to it, to this globe over here, what do we see on that globe? Newton's collier is inscribed on it, not the equations of the Principia or of the calculus, but Newton's collier. And I think with that, I will stop and turn it back over to the hosts. Thank you.
Okay, well, thank you. Thank you very much, Jed. Okay, so this talk is open to questions, and we have a few questions coming in here. Let me take a look here. Okay. Actually, one of the questions was, early on in your talk, you mentioned that Newton evolved a way to say how civilizations evolved, and he had the kings evolving from ordinary people. So what was his view of the divine right of kings and the divinity of monarchies, etc.?
Oh, I don't think Newton thought anything of the divine right of kings, frankly. I mean, he was, of course, a monarchist, but within the overall grounds of what had evolved into a constitutional monarchy, or was becoming more of that after the Glorious Revolution and the removal of James II. And he certainly didn't think the deity reached down and empowered kings with any sort of divine imprimatur. That would run completely contrary to the way he thinks.
One of the questions was, in Newton's early life, was there any indication of this genius that he had? I mean, when did this become apparent?
Well, we don't know all that much about his early years, although the house he grew up in can be visited still. You can go there and you can even see the room where he probably did some optics experiments and so on. And he went to a grammar school in the town of Grantham. We know a little bit. We know that he liked making things. I mean, there are stories that were told later on about such things as he would fly a kite at night and he hooked it up with candles and so on and scared the living daylights out of people who thought it was some kind of strange cometary appearance foretelling disaster and so on. We know he liked to build and make things. We don't have much evidence that he was showing any interest in mathematics, not that he would have been taught much about that, except arithmetic and so on. But he did have, his mother had acquaintances. Originally, he wasn't supposed to be going to Cambridge. He was supposed to take care of the manor farm. In fact, there's a story that, you know, he's out in the fields thinking about something, supposed to be looking after the cows, and the cows come home and he doesn't. They get there before him and so on. And there was a relation, and he was reading books in libraries around and relations, and it was decided to send him up to Cambridge. But again, the first few years there's no really clear evidence that he was showing any kind of the sort of brilliance that he came to show subsequently. He had friends. He was not the solitary scholar it's often spoken of. We know he had friends and talked to people. And I think, or we think, my colleague and I, Modi Feingold, think that he's first sparked with this when he came into the encounter of the professor of mathematics, Isaac Barrow. And Barrow interrogated him about a number of things and came to recognize very quickly there was something unusual in this character. And it was probably through his interactions with Barrow that sparked his very rapidly developing interests in mathematics and allowed him to bring into fruition also his tactile desire to manipulate things that evolved into his experimental practice.
Okay. So this question is, given the accuracy of individual and identifiable stellar positions over the time Newton had access to, was Newton able to notice the proper motion of stars? If so, did he consider them as governed by the same gravitational laws as he saw the sun and the planets, etc.?
I don't know that there's any remarks that he ever made about the proper motions of the stars, actually. And he certainly never made any remarks about interactions, gravitational interactions between the stars, although if he were sitting here and we'd asked him, talked to him about it, he'd almost certainly say, well, there must be. But I mean, observations are pretty cruel. Let me put it to you this way. His great rival Hooke, and Michael Nauenberg and I had a lot of discussions about Hooke, which is, of course, as you heard, Michael's great discovery. Hooke had actually, he worked as demonstrator of the Royal Society. He had to show experiments. He'd actually tried to, he built this huge telescope where he cut holes in the roofs of where he was living to try to measure what we call stellar parallax, namely the visual shift of a closer star, presumably against the background of other stars as the Earth moves from one side of its orbit to the other side. He couldn't actually measure that. That was only measured in the 1830s because it's tiny. And it was only in the 1720s that the astronomer John Flamsteed, doing somewhat more careful observations, observed a strange shift that we now call stellar aberration, which is due to the relationship between the velocity of the Earth in its orbit and the velocity of light raining down upon the Earth. So anything about stellar proper motions and so on in there, no.
Okay, a couple of questions about your relationship with Michael Nauenberg. You mentioned at the beginning that you had some discussions, there were things you agreed with him on and things you did not. Any of that you wish to relay to us?
Michael was one of the best people I have ever known. And I'm old now, I've been around a while, to discuss, argue, work with, and come back and forth with on complicated technical issues, because he worked on complicated things. The Hooke material is one thing, deeply significant in its way. He opened that up. But it wasn't only Hooke. He actually made an argument concerning something very fundamental in the way Newton had worked with his mathematical techniques to analyze orbital motion. Now, I mean, one point I should make about this, because this is relevant for what Michael did, Newton never actually demonstrated that an inverse square law will produce orbits that are conic sections. What he and everybody else was interested in at the time was the reverse, which was called the direct problem. That is, assuming, for instance, that the planets orbit in ellipses, which are produced by a force directed to a focus of the ellipse, what would be the form of that force? Michael argued, actually first demonstrated that using a technique which is completely different from the one that appears in the Principia, and that what Hooke's influence was suddenly showing Newton that there might be another equally valid but much more manipulatable technique for solving such problems. And that Michael and I spoke about often. And at the moment, my colleague Moti Feingold and I are writing a new book on Newton's early work on impact, motion, and so on. And a central portion of it is going to be a claim grounded on manuscripts that Michael was right.
Okay, very interesting. Oh, as you're showing us these manuscripts, etc., as a historian, how much of this is now digitized? It's searchable. I mean, when you were doing this research, did you have to go in and decipher these manuscripts, or has some of this been done for you?
Okay, well, first, when we were first doing this, and in fact, most everything that I've ever worked on that always involves manuscripts, if you were lucky, there were microfilms, but microfilms are crude. And when Modi and I were first working on this, we had to go to the Bodleian Library where the manuscripts were. And they wouldn't even though I even then had a little digital camera, they wouldn't let me use it. So I had to open my computer with the images from the microfilm that I digitized. And where I couldn't read what was on the microfilm, I had to page through with a magnifying glass and look at the manuscripts and then type it in on the computer. Now, not only is it digitized, but they have been, Newton's works have been imaged at very high resolution. They're available on the web for scholars to work with. And so that's what I work with now. I don't have to go to Cambridge to see it all. Not everything has been digitized by any means, but a lot of it has. And it's opened a world of scholarship.
Is it searchable?
No, you have to still figure out what it's all about.
Okay, and one of the comments here was amazing erudition. How much time did you spend studying Newton? Obviously a lot.
Well, it was my own work had been in more modern things on electrodynamics and optics, and it was my colleague here when he arrived here at Modi Feingold, he got me interested in this problem, and we were away. Diana, my wife, who's a professor here, she's general editor of Einstein's papers. We were away and in Holland, where I was invited to be a professor for a few months in the physics department in Amsterdam. And while there, I started doing these computations and working with the manuscripts. So I think it took about 4 months before I could see any possibility of getting into it. And then it took about 8 years after that.
Okay. Well, we've about come to the end of our time. So we're very grateful to you, Jed, for being our inaugural lecture in this Michael Nauenberg History of Science program, a program that we hope will continue. And so even though it wasn't quite the in-person meeting we were hoping for, we still enjoyed it very much. Certainly not your fault. These are just our times. And in the chat, I have put a links. If people want to contribute to sustain this fund that we have to support this lecture, there's a link that will allow you to do that. So thank you, Jed. Thank you, Tony, for your introduction. Thank you for all the participants. Thank you to the Nauenberg family. And we hope that this series is going to continue in the great vein at which Jed has started it off. All right, so good night, everybody.